Class, grading. Everyone is doing okay in class? Everyone getting A? Don't break my record. All the students get A in this class. If you are not getting A, then you are really working hard not to get a grade. Anyway, that being said, in today's class, I'm going to talk about worm and wormwheel design. I will give you the design steps, and then we will start talking about internal combustion engines. So I will talk about some theory concepts in how to design an engine. What are the difference between 4-stroke and 2-stroke engine? What is the difference between a gasoline and diesel engine? Probably in thermodynamics 1 or 2, you must have seen these power cycles like diesel cycle, dual cycle, Otto cycle. Now, all those theoretical material that you study in thermodynamics, how do we take all that information and actually build a mechanical device that will convert fuel energy into useful work? So I'm going to talk about that. Also, I don't know how many of you are into European cars like Audis or Mercedes-Benz. Yeah. So there is, Lotus cars. There is a car company which is called Lotus car. Lotus car, they have a fantastic engineering design center, and they have developed these different softwares for engine design, powertrain design, and so on. So there is a software which is called Lotus Engine Simulator. So Lotus Engine Simulator, we will use that software to design single cylinder internal combustion engine. So in today's class, I'm going to talk about worm and wormwheel. Then I will talk about few basic concepts in internal combustion engines, and then I would actually direct you, I'll show you where to download the software, and then we can actually start discussing design of internal combustion engine components in next class. Okay, no questions? Anyone? Any questions from anyone? If there are no questions, I will jump on to design of worm and wormwheel. So worm and wormwheel is used when you want the power transmission to be unidirectional. Unlike spur gear, helical gear, bevel gear, power transmission could be from drive shaft to driven shaft, but you can actually it can go the other way as well. So in worm and wormwheel, for some reason my Apple Pencil is not working. Something is not right. Just bear with me for a second. Okay, unfortunately, my Apple Pencil is not working. So okay, finally. So in Wormwheel, what we have is we have a wheel, also called as Wormwheel. And we have a worm. Now this worm is exactly similar as a power screw. So if you recollect, we studied the design of power screws. So worm is nothing but a power screw. And wheel is a gear. So a rotation of worm will cause wheel to rotate. But please understand, the advantage of worm and worm wheel is when you rotate the worm, the wheel rotates. But if you rotate the wheel, the worm is not going to rotate, which means the power flow or the power transmission is only in this direction. So you cannot transmit the power from wheel to the worm. So that's why if you have a worm wheel type of mechanism, it is commonly used in hoisting or lifts or elevators. And the reason for that is, imagine you are lifting a load and all of a sudden the motor that is connected loses power supply. So this is the motor. And then you don't want that load to run down on its own. You want that load to be sort of braked. So worm wheel, because of their configuration, they provide this fail-safe type of arrangement. So these are important points. So please understand, the worm wheel is a unidirectional mechanism. So the power transmission is only from one direction. So if you rotate worm, if worm rotated, wheel rotates. But if you rotate wheel, worm does not rotate. That's why the application is in hoisting. So worm design is similar to power screw design. So the worm, if you were to look at sort of zoomed view, you will notice it would look something like this. So clockwise rotation will give you advancement to one lead. So what are the important parameters of this gear assembly? And we borrow the same concept from power screws. So for worm, what we have axial pitch, which is also called as the linear pitch, which is given as PA. And remember, in power screws, we talked about the concept of lead. Lead is advancement in one turn, and lead is equal to axial pitch multiplied by n, which is number of starts. Next concept is the lead angle. Usually the lead angle is from 9 degrees to 45 degrees, which is tan inverse of lead divided by pi times diameter of the worm. Now, just to give you sort of a pictorial view, we talked about the same concept in power screws. This is the lead. This is pi times diameter of worm. Now, there is concept of tooth pressure angle. So, next concept is tooth pressure angle. And tooth pressure angle depends upon lambda, which is the helix angle, and tooth pressure angle is phi. So here is a table that is used for different values of lambda. You are going to have different values of tooth pressure angle. So as you can see, the helix angle, the lead angle, or again helix angle, can go from 9 degrees to 45 degrees. So typically, when the angle is less than 16, the tooth pressure angle is 14.5. When the angle is from 16 to 25, the pressure angle is 20. When the angle is 25 to 35, the pressure angle is 25. And when the lead angle is 35 to 45, the angle is usually 30. And this table is the design data table. That table is given in chapter 31, table 31.1. Then the next concept is the normal pitch. Which is Pn is equal to Pa times cosine lambda. Next concept is the velocity ratio. And velocity ratio is n worm divided by n wheel. So that is nothing but diameter of wheel divided by diameter of worm. Once again, wheel is this big gear. This is D wheel. And this, if you look at the side view, this is diameter of worm. So the other equation that you can use to find velocity ratio is number of teeth on wheel divided by number of starts on worm. So number of teeth on wheel divided by number of starts on worm. So just like power screw, you can have single start worm, you can have multi-start worm. So you can use any of these equations. Now, in the most important thing is whenever you design, you cannot randomly design worm and worm wheel. Worm and worm wheel is typically designed as a pair. So whenever you are going for worm wheel design, so worm wheel design, it is based on worm design. So what are the important dimensions when you are designing this worm and worm wheel? So say you have normal pressure angle, which is typically 14.5. You are going to have outside diameter, which is usually dg plus PC, where PC is circular pitch. Then you would have something called as the throat diameter. So you're going to have throat diameter. It's usually 2.5 times circular pitch. Circular pitch is pi times module plus some clearance. Then you're going to have gear face, say radius, which is 0.8 times PC plus some type of clearance. Then you are going to have gear rim, which is 2.2 times PC plus 14. Now the major problem with worm and worm wheel is the efficiency is low. Since the efficiency is low, that results into high power loss. And whatever power that we lose, that is converted into heat. So basically Q, which is the heat generated, is equal to 1 minus efficiency multiplied by power input. And that must be equal to H times A times delta T, where A is the surface area. This is the heat transfer coefficient. And this is change in the temperature. So let me give you the design steps for wormwheel design. And it's basically, when you look at the wormwheel design, it is similar to the power screw and gear design. So think about this like you are designing a power screw and you are designing a gear. So when you design a power screw and you design the gear, that is how you are going to design a worm and worm wheel. So basically, worm design is similar to the power screw, and worm wheel design is similar to the gear. So one thing I want you to understand is in worm wheel, this is slightly unique. Almost always the wheel is weaker. Worm is stronger. So why worm is stronger? Because it's like a solid shaft and it's like a design as a power screw. So it is customary to design the wheel first and then using the wheel dimensions, making sure that the wheel is strong, then transfer the appropriate dimensions onto the worm and design the worm. So when you design the worm wheel, unlike gear and pinion, we first try to find out whether the gear is weak or pinion is weak. In this case, we will say the wheel is weaker than the worm. So as wheel or worm wheel or gear is weaker than worm or power screw, we design wheel first. And this design is similar to the spur gear design. Spur gear design. So what is step one? Step one is find out the value of WT. WT is equal to power divided by pitch line velocity multiplied by the service factor. So P is equal to power, Vp is equal to pi times diameter of the wheel times N divided by 60. CS is the service factor. Once you find out the value of WT, this value of WT has to be equated to sigma naught times CV multiplied by B multiplied by pi times M multiplied by Y. And CV is nothing but 6 divided by 6 plus V, where V is nothing but Vp. The next step is Y is the Lewis's form factor. Y is equal to 0.124 minus 0.684 divided by T when the pressure angle is 14.5. Y is equal to 0.154 minus 0.912 divided by T when the pressure angle is 20 degrees. Now, the tables that you're going to use to find sigma naught, they are the same as spur gear tables. The proportion B over M ratio is same as the spur gear. So you can assume B by M to be anywhere between 8 to 12. So which means after solving this, you would land up with an equation for M. So you will know what the module is. So at the end of step one, you should find out module. Then we have to find out something called as the dynamic load. Now, believe it or not, finding dynamic load in the case of wormwheel is extremely simple. How do you find out dynamic load in the case of wormwheel? So WD, so step 2, WD is equal to dynamic load is equal to WT divided by CV. WT divided by CV. So CV is the same velocity factor, 6 divided by 6 plus V. This is the same velocity factor. That will give you the value of WD. Step 3 is you have to find out static load. So step 2 is dynamic load. Step 3 is static load. Static load is WS. What is the difference here? The difference here is you are going to have sigma E times B times pi times M times Y. Now sigma E is the endurance strength. And please note, this is not the surface endurance strength, but this is the core endurance strength. And typically, when you are looking at wormwheel design, worm is made up with steel. Usually the worm is made up with steel, and the wheel or the gear, it typically made with cast iron or prosper bronze. And here is the reason why. Because when you have steel to prosper bronze, the coefficient of friction between those two contact surfaces is significantly lower compared to steel and steel. And the other thing that happens is when you have steel coming in contact with prosper bronze, after some time, basically those two wear into each other. So let me give you a very simple example. Initially, it's like breaking in. So when you buy a new car, they don't go beyond 60 miles an hour. Initially the mileage of the car is not very high because the components are not sort of broken in. After some time, after some usage, what happens is those components kind of wear each other out to the point that the functioning is much smoother. So initially, when you would see is coefficient of friction is high, after some time breaking in, the coefficient of friction stays low, and with proper lubrication, you want to maintain those two components at that low coefficient of friction. So same thing happens in the case of worm and wormwheel. That's why you have the worm that is made up with steel, and you have the wheel that is made up with cast iron, which is softer than steel, or prosper bronze, which is again softer than steel. So sigma E values typically for cast iron is given as 68 Newton per millimeter square. For prosper bronze, so PB is given as 168 Newton per millimeter square. And you want to make sure that whatever WS you find is greater than WD for the design to be safe. Then next step, step 4, is concept which is called wear load.
So how do we find out the wear load? WW is diameter of the wheel multiplied by B multiplied by K. And basically DG so DG is the wheel diameter, B is equal to the width, and K is called as the load stress factor. And this load stress factor is given in table 31.5. So there are combinations. If you have worm, if you have wheel, then this is, let's look at the combinations. If your worm is made up with steel, wheel is made up with prosper bronze, K factor is 0.415. If your worm is made up with cast iron, the wheel is made up with prosper bronze, then the K factor is 1.035. And then again, for the design to be safe, wear load has to be greater than the dynamic load. Next step, which is step 5, is checking for heat dissipation. And Q generated is 1 minus efficiency multiplied by power. So there is a chart in the textbook. So if you look at the textbook, quickly look at the efficiency chart, and there is a big long expression for efficiency calculation. You can use either the equation or you can use the values in the chart. So look at, I'll tell you, yeah, so, and you can find out the equation for efficiency. So efficiency so look at the equation for efficiency, which is tan lambda cosine phi minus mu, which is the coefficient of friction, tan lambda divided by cosine phi tan lambda plus mu. So this is the equation that you can use to find the efficiency. Alternatively, let me give you an approximate equation. Is 1 minus mu times tan lambda divided by 1 plus mu divided by tan lambda. So mu is the coefficient of friction, and depending upon whether it's, usually the coefficient of friction will be somewhere between 0.2 to 0.3. So again, you can use the either empirical relationship, or you can look at the design data, and then you can get the appropriate value of lubrication coefficient of friction.
Again, coefficient of friction depends upon the type of lubrication that is available. If you are running the worm wheel through a continuous lubrication, then your coefficient of friction can go all the way to 0.02. So mu 0.02 for lubricated worm wheel. And again, if you look at page, this information is given on page 1108, and you can actually so worm wheel, they have lot of applications, and depending upon what you're trying to achieve, you can use the appropriate gearing design. The most important thing about the worm wheel is the shafts could be perpendicular to each other, but they don't have to be in the same plane. So for an example, if you look at the configuration diagram of worm wheel, the center line of the worm is perpendicular to the center line of the wheel, but these two center lines are not in the same plane. If you look at the spur gear, center line of the shafts are in the same plane. Helical gear, center line of the shafts are in the same plane. Bevel gear, the center lines are perpendicular, but still the center lines are in the same plane. But in the case of worm wheel, the center lines are not in one plane. So this is the overall design procedure for worm wheel. And that's pretty much it. So I think you should be able to solve a worm wheel design problem. Then you want me to solve a problem, or you guys okay? Yeah.
Once we calculate the Q generated, what do we do?
Oh yeah. Oh, sorry, I didn't complete. Thank you. So Q generated, you have to make sure that Q generated is less than Q dissipated. So which means the heat dissipation capacity. And that equation is H times A times delta T. So H is the coefficient of heat transfer, and the coefficient of heat transfer, again, it depends upon whether it's a free convection or if it is forced convection. So you can use the appropriate coefficient of heat transfer. And if you want to look at what should be the coefficients of heat transfer, that can be taken as 378 H is equal to 378 watts per meter square degree Celsius. And then area is the area of housing. So A housing. And for practical purposes, you can say that it is same as pi by 4 diameter of wheel pi by 4 d square, which is the diameter of the wheel. This is approximately. And delta T, and depending upon what application you are looking at, it should be anywhere between 20 degrees to 40 degrees. So what you can do is you can substitute the value of H as 378 multiplied by, then you can substitute pi by 4 diameter of wheel square multiplied by, let's say, 30 degrees.
and then you will find out the value of QD. And this heat dissipation capacity should be greater than heat generated. So that means that design is safe from thermal considerations. So if you have the textbook, all the information about the data that you need to design the wormwheel is given in the textbook. And we will follow this recipe that I gave you, and we will find out the different dimensions of worm and wormwheel. Are you with me so far? Okay. Do you want me to work out a problem, or should we start discussing the design of internal combustion engines? Okay. Work out a problem? Everyone okay with that? Okay, I will work out a problem. So, any questions from my online students before we proceed? So this problem is power transmitted is 1.1 kilowatt. Transmission ratio, which is the velocity ratio, is equal to 27. The worm RPM is equal to 1440. So worm is made up with steel, worm, and wheel is Prosper bronze. Teeth, pressure angle is 20 degrees involute. Now, what we want to do is we want to find out the dimensions of this gear. Now, in some problems, they will give you the distance between the worm and wormwheel. Now, please understand. So, in some design problems, what they will do is they will give you the distance between the center line of the worm and the center line of the wheel. So this distance will be specified. But in this particular problem, the center distance is not given. So what that means is we have a lot more flexibility in terms of designing worm and wormwheel. So what I'm going to do is I'm going to assume, and this is just an assumption because center distance is not given. So assuming center distance is equal to, say, 100 millimeter. Now, based on the center distance, there is an empirical relation, and I'll tell you where that empirical relation is given. So based on the center to center distance, you have figure 31.7 that kind of gives you the design curve for wormwheel, and that is where you have this empirical relation that gives you diameter of the worm is equal to x 0.875 divided by 1.416, where x is the center distance. So 100 0.875 divided by 1.416, and that gives you about 40 millimeters. And I want you to look at the textbook. If you have the textbook, this relationship is described in a pictorial form. This relationship is also given as an equation. So this equation, so this is given in page 1106, and you can refer figure 31.7, which is worm gear design curves. So with that, we can find out the approximate diameter of the worm. Now, once we know the diameter of the worm, half of the battle is done. So this distance is going to be 40 divided by 2. This distance is 100. So what that means is the radius of the wheel is going to be 80 millimeter. That means the diameter of wheel is equal to 160 millimeter. Now, since the velocity ratio or the transmission ratio is 27, so transmission ratio is equal to 27. I want you to go to table 31.2. If you have the textbook, please go to table 31.2. And on table 31.2, you have velocity ratio, which is same as the transmission ratio. Velocity ratio is 27. And for 27, it will recommend, do you want to use the single start worm or do you have to use the multi-start worm, which means do you want to use double start, triple start, or quadruple start? So one thing I want you to understand here is typically if the velocity ratio is very high or the transmission ratio is very high, then you use a single start worm. But when the velocity ratio is somewhere between 12 to 36, you have a choice to go to a double start worm. Again, if your velocity ratio is between 8 to 12, you can use a triple start worm. And this all information, it comes from table 31.2. So here, since the velocity ratio is 27, that is in between 12 to 36, we can use a double start worm. So we will use a double start worm. Now, with that, we can find out the number of teeth. So remember the equation for velocity ratio. Velocity ratio is equal to number of teeth on wheel divided by number of starts of worm. Since velocity ratio is 27, number of teeth is going to be 54. Now, next step is to find out the axial pitch. To find axial pitch, which is equal to the relationship that we have already discussed, which is the circular pitch. So let me, axial pitch is equal to, so axial pitch of worm is circular pitch of the gear. Now this, I kind of briefly talked about it, but let me explain what that means. So at the end of the day, what you have is, think about it like you have a power screw. And this power screw is actually meshing with a gear. Power screw is meshing with the gear. So I want you to understand that the axial pitch of this guy, this is the axial pitch of this guy, which is PA, has to be the circular pitch of this guy. So the axial pitch of the worm has to be the circular pitch of the wheel. Only then the worm would mesh with a worm wheel. Otherwise, the worm is not going to mesh with worm wheel. Everyone understood this? So it is like, think about, imagine that you have a gear and you have a power screw. And this power screw can only mesh with the gear if the circular distance or the circular pitch is same as the axial pitch of the worm. So the axial pitch of the power screw is same as the circular pitch of the wheel. And that equation is pi times module, so which is pi times diameter of wheel divided by number of teeth. And please note, we already have these dimensions, pi times 160 divided by 54. So the axial pitch is 9.3 millimeter. And since we know the axial pitch 9.3, I can just do module is dw divided by t, and that gives me about 3 millimeter. So with that, I have some basic dimensions already worked out. And what I'm going to do is I'm going to find out the value of B, which is, this is an empirical relationship, 0.73 dW, which is the diameter of worm, 0.73 times dW is 40 millimeters. So you get about 28 millimeter. Now with that, we are ready to do the wheel design. So step 1 in wheel design is we want to find out CV, which is 6 divided by 6 plus VP, and VP is equal to pi times DG NG divided by 60, and that is 0. So pi multiplied by 0.160 multiplied by speed. Speed is 1440 divided by 27, because this is the speed of the worm speed. This is the velocity ratio. So divided by, you can actually use 60, and that will give you meters per second. substitute this, and then you are going to get 0.93. Lewis's form factor, y is 20-degree involute, so 0.154 minus 0.912 divided by Tg, which is 0.154 minus 0.912 divided by 54, 0.137. Then, since we are going to use Prosper bronze, for Prosper bronze, sigma O is equal to 84 Newton per millimeter square. So Wt is equal to sigma O times Cv times B multiplied by pi times M times Y. So I would substitute 84 multiplied by 0.93 multiplied by, please note we already found B, pi, M is 3, 0.137. So that gives me 2825 Newton. Now, a word of caution. In this problem, since the center distance was not given, we actually started with an approximate center distance, and that center distance allowed us to compute the diameter of the worm. Diameter of worm gave us the diameter of the wheel, and since the velocity ratio was given to us, number of starts we found out from the velocity ratio, we directly found out the diameter of the wheel, number of teeth, and the module. Now, what we want to check is this. For the module that we have found out, for the material that we have selected, what is the power transmission capacity of this worm and worm wheel? And if the power transmission capacity of this worm and worm wheel exceeds the power that we need to transmit, then the design is safe. So please try to understand, when you design, there can be multiple approaches. So in this case, what we did, we added some geometrical constraints. Based on the geometrical constraints, we found the dimensions, and now we want to find out what is the power transmission capacity for those dimensions and for that material. So what I want to do is, Wt we found out is 2825. So what is the power transmission capacity? So Pc, which is power transmission capacity, which is Wt multiplied by Vp, which is 2825 times 0.452. That gives you 1277 watts, which is 1.27 kilowatts, which is greater than 1.1 kilowatts. That is the power transmission that is required. Step 2 is we have to check for the dynamic load. So dynamic load, and dynamic load is nothing but Wd is equal to Wt divided by Cv. Wt is 2825 divided by 0.93, which is 30038 newtons, and that gives me the power dynamic, which is Wd times Vp, which is given as 3038 multiplied by 0.452, which is 1.37 kilowatt. Now we want to find out the static, step 3. So static load, and that sigma E is 168 Newton per millimeter square. Ws is equal to sigma E multiplied by B multiplied by pi times M times Y. So 168, 28 pi times 3 times 0.137 to get 6075. As you can see, this 6075 Newton is significantly greater than WD, hence design is safe. And the last step is step 4, is find the wear load. Wear load K factor from the table is 0.55. So this comes from table 31.5, and you can find out the value of wear load as dg b times k. dg is 162 times b is 28 times k is 0.55 is 2495 Newton. And then what you can do is, there is something that I need to tell you. So dynamic load is 3038. But the wear load is 2495. What this means is this design would fail in wear, since WD is greater than WW, design fails. So I just want to tell you that if you look at this problem worked out in the book, they got this step wrong. So they say that it is safe. It is not safe, because in this case, the wear load WW is less than the dynamic load, which means this gear, this design is going to fail. Now there are two choices at this point, and I will explain you what the choices are. So before I discuss what the options that we have in front of us, I just want you to make sure that understand the wear load is less than the dynamic load. However, this dynamic load was found out from the dimensions of the gear. So if you think about it, the dynamic load, what it tells me, dynamic load is capable, the power to be transmitted is 1.37 kilowatts. But the actual power that is to be transmitted is nothing but 1.1 kilowatt. So if you see, the power to be transmitted is 1.1 kilowatt. So you can do a recalculation here to change the values of the dynamic load, and then see if that change in the calculation gives you slightly less dynamic load, or alternatively, at this point, what you can do is, the easiest way is increase the value of B. So basically, increase B. So what would happen if you increase the value of B? If you were to increase the value of B, the consequences if you look at the static load equation, this B also appears in the static load equation. So clearly your static load capacity is going to increase. But right now your design is already safe for static load. So even if you increase the value of B, that's all good. Everyone understood this? At this point, the design is failing. We cannot change the diameter of gear. Why can't we change the diameter of the gear? Because the center distance is fixed. You cannot change the diameter of the gear. So the only K factor, it depends upon the materials that you cannot change. So if the material was not specified, then you can just say, I'm going to use a different material, change the value of K, and then find out the wear load that is greater than the dynamic load. But in this case, the materials are specified. So here you can increase the value of B. So for example, our value of B was 28. So I'm thinking if I change this value of B to maybe 35, the design is going to be the same. So what I would do is at this point, I would just make a note, since the design is failing, we would increase the value of B. So B new is equal to 35. And can someone tell me what is the value of WW for this B new? Quickly with the calculators. $3,118. So this is greater than the dynamic load. So our design is safe. Yeah.
What is wear load and how does it fail?
So what happens when two objects come in contact? There is something called as contact stresses. They are also called as Hertzian stresses. They come in contact because basically one surface, think about the gear coming in contact. When the gear is coming in contact, it's not sort of an area contact, but it's the one gear is scraping the other gear, which means you are going to have very high localized stresses. Now, what would that localized stress do? That localized stress would cause some type of localized deformation, and this continuous deformation on the contact surface would result into pitting. What is pitting? Pitting is microscopic removal of material. So that's why you would notice that when the two gears, they mesh, after some time, when you look at those two gears, they become shiny. Why they become shiny? Because one gear is scraping the other gear. And this wear load tells you the maximum load that contact surface can resist before there is pitting. So before that, there is small material removal. So that's why what you notice, if you notice a gear, a used gear, if you kind of try to see what the surface is, you will see some macroscopic tiny dots on that. So those dots are basically because of the pitting that actually takes out the microscopic material, and gradually that deepens, and then the crack initiation would start where those pits are. Everyone understood this? Any question? So wear load is what is the maximum amount of load that contact can sustain. That is the wear load. Dynamic load is load because the load is not static, it's continuously changing. So basically it's not like static load, it's like there is velocity involved. Basically the loads, the material is sort of fatigue, loaded in, loaded out, loaded in, release, loaded in, loaded out. So that's why. Any other questions from anyone? So last part is step 5. Is you want to find out Q dissipated. Q dissipated is nothing but 1 minus efficiency multiplied by power. Now efficiency, you can find it from the equation 1 plus, I think I gave that equation, 1 minus mu tan alpha, tan lambda, 1 plus mu divided by tan lambda. And I'm going to assume mu as 0.02, say lubricated, and 1 minus mu. What is the value of lambda? They gave us the axial pitch, right? So lambda is equal to tan inverse of lead divided by pi times diameter of worm. So lead, since it's a double start, multiplied by axial pitch divided by pi times diameter of worm, tan inverse axial pitch. I think we found axial pitch somewhere. What is the axial pitch? Yeah, axial pitch is pi times m, which is 9.3, 2 times 9.3 divided by pi times diameter of worm. What was the diameter of worm? 40. Can someone quickly tell me what is the value of lambda? After that value of lambda, you can substitute and find out the value of efficiency, and then Q generated and Q dissipated is 384 times pi by 4 diameter of wheel square multiplied by 40, and just make sure that QD is greater than QG. With that, your wormwheel design is done. Any questions? Online students? So I just want to, before we conclude for today, next time I'm going to talk about the internal combustion engine design. So I want you to install a software. Go to Google and say Lotus engine simulation. So Lotus engine simulator, and go down. This is the engine, and they have multiple products. They have the power transmission design, they have the valve train design, they have the suspension design, they have lot of stuff. But what I want you to do is, here is Lotus engine simulator software that is available to download. So please download this, and this is a very good software. How many of you have played Angry Birds? Have you played Angry Birds? Okay, since you have played Angry Birds, you can use Lotus simulation software. It is like grabbing the blocks, cylinder block, grabbing the valve train block, grabbing the fuel block, grabbing the, either it's a direct injection or it is like a carbureted engine, the carburation block, configuring those parameters of the block,
and the software will do the CFD and other simulations inside and give you the expected power capacity, the power curves, the brake mean effective pressure, and all other performance parameters that you need. This is the first step. The big brother of this software is called Ricardo engine simulation. And that's a huge piece of software. But as far as this course is concerned, I'm going to teach you how to design an engine using back of the envelope mechanics of material calculations. And then I will show you how to use the Lotus engine simulator software. If you know this, you are welcome to put that in your resume if you want to apply for jobs at Ford, Chrysler, GM, Nissan. I don't think Tesla it would work, but you can apply that. You can say, I know how to use Lotus engine simulator software. With that, I'm gonna stop here, but don't forget it's a 15 MB, 16 MB software, and there is help file and tutorials that also will help you. With that, I am gonna stop recording